welcome back, and in this presentation we're going to talk about bond enthalpies. So let's talk about the breaking of those bonds. In any chemical reaction we have two things going on. First, we have the breaking of the bonds between the atoms of the reactants, of the original chemical, and then in the second step the forming of new bonds as the new chemicals form. Now, if we talk about the breaking of the bonds, this is always an endothermic process. It always requires an energy input to break those bonds, but why should that be? Well, what is a chemical bond? It is that attraction of two atoms to each other, attracting between the positive nuclei of those atoms and negative electrons held in the center, an electrostatic attraction. Moving them apart against that attractive force is doing work against the electrostatic attraction, and for that requires an input of energy. So how do we get exothermic reactions? Well, in those situations there is always a difference in the amount of energy that is required to go in to break up a reactant and the amount of energy given off when a new product forms. You see, if I broke something up and the same thing formed, it would give out as much energy as was taken in. But if I form a different chemical, then I could have the new chemical release more energy from its forming bonds than was required to break the originals. That would be exothermic. And of course the opposite is true. I could find that I put in a lot of energy to break the bonds, and the ones that form do not give out nearly as much as what I had initially invested, and so therefore it would be endothermic. Now, in the breaking of bonds, we call this the average bond enthalpy, the amount of energy required to break 1 mole of a specific type of bond in the gaseous state. Now, for this here, it may not naturally be that the object is in the gaseous state naturally. At the particular temperature, you might find that it is supposed to be a liquid or a solid at that temperature and pressure. And so this average bond enthalpy imagines that they're all gaseous molecules, and because that is not the natural state, we can't claim that this is under standard conditions, because that is not the standard state. But what we can do is we find that it is quite useful to give this thing the average bond enthalpy. It tells us just how much heat energy needs to go in to break that particular bond. But not all the time. You see, the actual amount of energy required to go in, it actually depends on the environment of the bond itself. If we look at the carbon-hydrogen bond in methane, for example, it takes 439 kilojoules per mole to break those. Whereas on the outer edges of a propane molecule, what you might find is those carbon-hydrogen bonds take 422 kilojoules per mole, and whereas the two hydrogens that are attached to the middle carbon, they only need 411 kilojoules per mole. Not requiring nearly so much energy, they must be more loosely held. Let's have a look at these enthalpy flow diagrams. So the first one is an example of an exothermic reaction. We have got unattached atoms or ions at the top, and we've got attached together. I've got lattice written there, but it could be molecule. It could just be after some chemical, some compound, after a bond has formed. And you can basically see that when they're separate, they have higher energy than they do when they're together. Now, if we look at the two processes, the side on the left, which is going from basically whatever the reactants were to go into the broken up state, the top line, and then how much energy we get back when the new chemicals form. New chemicals are on the bottom line. What we see is that here, more energy comes out making new bonds than went in to break the original bonds. And so therefore there is a small negative amount of enthalpy there, and so you can see that basically the chemicals have lost some energy lost to the surroundings, so this is exothermic. In the second diagram, what we start with is at the very bottom, that's the chemicals joined together, what I've called the lattice, but it could be a molecule. Those bonds breaking, there's far more energy has to go in to break those bonds to make them into the ions. Those ions then going on to form new chemicals, which is the intermediate step on the right hand side. You can see that more energy had to go in to break the bonds than was giving out making new bonds. and it means that the enthalpy change was positive, which means it's an endothermic reaction. There was a net input of energy, and you can see that there's a net input of energy because that small intermediate platform where the products are is higher in energy than the bottom line, which is where the reactants are. On the right hand side, I've written down all of the average bond enthalpies for the common bonds. You don't need to know these, but it is useful to understand how to apply them. So let's have a look at that. So the enthalpy change of a reaction is given by the sum of the bond energies in the reactants minus the sum of the bond energies in the products. So if we had a look at a reaction, this is the combustion of propane, and what I've got there is the balanced formula. What we need to do is draw their structural formulas, and so I've drawn them underneath, and I've multiplied them so I've got the correct number of molecules. This is really key. It's going to be really helpful later. You can see I've got 5 O2s there, I've got 3 CO2s, and I've got 4 H2Os and 1 propane. And what I need to do is I just simply need to multiply how many bonds there are by the enthalpies of those bonds. So I've got 8 carbon-hydrogen bonds in propane, I've got 2 carbon-carbon bonds, and I've got to add those to the 5 oxygen double bonds that I see on the oxygens there. Now this is the sum of the bond energies of the reactants, and I must take away from these the sum of the bond energies from the products, which I've got right there. And you can see I end up with an answer minus 2054 kilojoules per mole. And so therefore this is an exothermic reaction, and of course it is. Combustion is always exothermic. It always makes a large amount of energy release into the environment. It's fire after all. So here are some examples to try. And so what we've got is an alcohol here. It's propanol, and no, it's not. It's ethanol, and it is being burnt in oxygen. And so that's quite simple. What you just need to do is draw the structural formula and then add the sum of the products bonds and enthalpies, and then take away the sum of the reactants bond enthalpies. Now that's a straightforward one to do, and you should do that, but I want to show you one where there's a slight complication which you have to be careful for. First of all, when it comes to balancing equations, if you look at the equation below, this is propan-1-ol, and what you can see is it's combining with 9 moles of oxygen. That is the simple whole number ratio. That is the simplest balanced way we could get that formula. However, if you remember from the definition, the energy required to break 1 mole is not going to be calculatable if we run it through that formula, because you can see we've got 2 moles of this, that is propanol. 2 moles of propanol is not the amount of energy required to released from the burning of 1 mole. So what we must do is we must balance the formula, and then we must scale it down so that we're talking about 1 mole of the reactant that is being burned. So we would have to, instead of using 2 moles of propanol and 9 moles of O2, we'd use 1 mole of propanol and 4.5 moles of O2. You might think that's a bit weird, but we have to basically do it relative to 1 mole of the fuel that is being burnt. And so that's a slight thing, but once we understand, all we have to do is change the numbers in front, the multiplying factors in front of the particular bonds that we have when we're working out the sum. So here you can see the alcohols of various different lengths. This is the homologous series for the alcohols, and you can see that the chemicals are just getting longer by a carbon each time. And you can see that the enthalpy of combustion is getting a larger negative number. So it's going from a small amount of energy released into the environment into a much larger amount of energy released into the environment. But why should that be so? I mean, what we observe is the enthalpy of combustion increases, albeit negatively, with the length of the carbon chain. And that's because with longer chain hydrocarbons, there are more bonds that, when broken, will release more heat into the environment. It makes it more exothermic the longer those chains are.